Alright, so this video is going to be my submission for my part of Group 4 group project. Not Group 4. Group project number 4. I don't remember what my group number is, but I'm doing problem 1, which is I'm going to use Prim's algorithm for this one. I'll write this down. I'll write this up here. Oh, I need to do this first. I think that's how it's spelled. Whatever. I'm going to be doing Prim's algorithm to find the minimum spanning tree for this graph here. And yeah, let's get into it. So the first step is you're going to want to create a few lists of stuff. You're going to want to make this list on the right here that has a key for each of your vertices. I'm not really sure what the plural on that one is, but you're going to want to list for the key values of those, the parent values of those, and you're also going to want to make a list that's over here on the left, which is a minimum Q, so that you can easily find the minimum and then extract it. It's part of the algorithm. So once you have those, you're going to want to initiate all of them to infinity, the key values to infinity. Do that. And then you want to initiate the parent values to nil. Nil. And then you want to put all of your vertices into your queue, so A through F, just like it is in the graph. And then the next step is you're going to want to, let's get a decently sized eraser. Whatever node you're going to be using is your root node. Whatever vertex you're going to be using is your root vertex. You want to initiate that key value to 0. Alright, and now that we have that, we can start with the actual looping part of this algorithm that starts to do stuff. So first of all, we're going to want to find whichever node that's in our queue over here has the lowest key value. So right now the queue has all the nodes, so we just look through all the nodes, we see that A has the lowest value, 0. And that means we pop A out of there. Ooh, hello. So A is now out of the queue. And then we look at A's adjacent nodes, which if you look over here on the graph, it's B and C. So let's start with B. Keep things in order. So first of all, we want to look and see if B is in our queue list. So we see that B is indeed in our queue list. So that's one part of our if. And the second part is it also needs to be our edge that goes from A to B needs to be less than the key value of B. And the key value of B right now is infinity. And the A to B edge is 1. So that means this if statement is true, which means we're going to go in to it and do this. The parent value for B, we're going to make that equal to A, because we're kind of like in the A step right now, and we're looking at its adjacent nodes, so that's why we're using A. And then we also go to the key value of B and make it equal to this A, B edge, this guy right here, so that's equal to 1. So then, go to our eraser, we go to B's keep value, make that, I'm also going to erase the nil because we're going to change that also. So we go to B's key value, make that 1, which is that edge, and then its parent is set to A. Boom. And then that's the if statement. And then we go and do this whole thing again for A's other adjacent node, which is C. So get rid of that. So we need to check if is C in Q? It is, right there. So that's good. And then is our A to C edge that less than the key value for C right now? And the key value for C is infinity. And the A to C edge is 6, so 6 is less than infinity, obviously. So we go back into our if statement again, and we set C's parent value to A, because we're still in A. And then the key value of C is set to that edge, which is 6. So then we whip out our eraser. Eraser, please. Get rid of this. Get rid of that. And the parent value is set to A, just like B. And then the key value is set to 6. And then, boom, we're done with that if statement. And then we loop back. And then since A doesn't have any more adjacent, we went through all of its adjacent nodes. Then we can go back to finding the minimum value again. Let's get rid of those. And let's search for the new minimum. So we want to find the minimum value of all the nodes that are in Q, and A is no longer in Q. So we're looking through B, C, D, E, and F to see which has the minimum. So B is a 1, C is a 6, and then we got infinity. So B is going to be the least. So switch to red. B gets popped out, no longer in there. And then we're going to look at B's adjacent nodes, which is A, C, and D. So we'll start with A. So is A in Q? No, it's not. We removed it, so can't go into the if statement. And then we go back to the next adjacent node, which is C. Is C in Q? It is. It's right there still. And is the edge from B to C, that's kind of a 6, but B to C, which equals 3, is that less than the key value of C? Well, key value of C is 6 right now, and 3 is less than 6, so we go back into our if statement, which sets the parent of C equal to B. Oh my god, dude, stop with the 6s. Okay. And then the key value of C is set to this edge, which is equal to 3. So even though we already changed C, we can change it again if we find a better path, which we have. Let's go to that. So the new key is 3 instead of 6, and the new parent is B instead of A, because that's an easier way to get to C. And then, boom, that's for C. Make some more room here. And then the last edge, adjacent node to B, is D. So is D in Q? Yes, it is. And then is the B to D edge less than the key of D? That's supposed to be a Y. So BD edge is a 4. D is an infinity right now. So yes. So D's parent value set to B. The key value is set to 4, because that's that edge. So let's whip out our eraser, go over to D, erase it. So this is set to 4, This is set to be... Alright. So we've gone through all the nodes adjacent to B, which means we need to go back and find the minimum thing again. So now our Q only has C, D, E, and F. So let's look through C through F. C's a 3, D's a 4, and then we got infinity. So 3 is or C rather, is our new minimum. So let's take it out of our Q. And then we're going to look at the nodes adjacent to C. So let's start with A. Is A in Q? No, it's still not. X, so stop looking at A. B is the next one. Is B in Q? No, it's not. It's also gone. Don't need to look at that. Is D in Q? It is, still. It's supposed to be a check mark. And then the second part of that is the C to D edge, which is equal to 2. Is that less than the key value of D, which is 4? So yes, it is. So we go into our if statement. Let's give me that select, please. Clean this up a little bit. Alright, so we go into our if statement, which sets the parent of D equal to C, and the key value of D is equal to that edge, which is 2. So, just like we changed C earlier, we're going to change D again. Since we found a better path to get to it. Get to the writing. So, D's key value set to 2. Parent is set to C now. So, the path so far is B's parent is A. So, it goes like right here. C's parent is B, so then it goes down. And then D's parent was just set to C, so it's like right here for now. And you can kind of see, this is supposed to be a 1 here. It's kind of following those least numbers, trying to find the most efficient path. Oh, I forgot to do F when I did B. So let's go look at F real quick for B. I forgot that it had those big arcs that went around it. So we just updated D's values. Okay. So I missed a thing. We got to backtrack a little bit. So let's look at F. Is F in the Q? It is. Is the BF edge, which is equal to 2? Is that less than F's value, which is infinity, which it is? So F's parent value is B. Oh, that's a P equal to B. And then the key value of F is equal to that edge, which is 2. So let's update F. And then we write down our stuff. This is a 2. Parent value is B. Okay. Yeah, I missed that. Alright. Now, let's go back to where we're supposed to be in doing the things that are adjacent to C. So we did A, which isn't in the queue, so we didn't worry about it. B, which isn't in the queue, we didn't worry about it. D, we did that, we updated it. And now let's look at E. So is E in the queue? It is. Is the CE edge, which is 4, is that less than E's key value, which is infinity? It is. So we update the parent. It's equal to C. The key value of E is equal to that edge, which is 4. So let's go into E. Sorry if there's thumping outside. There's a lot of people that live here. So then we update this to 4. And then this to C. And then let's not we're done with E. So let's not forget about F again. So is F in the list, or in Q it is. Is F's key value less than the CF, so is the CF edge, which is equal to 7, is that less than F's key value right now, which is 2? It is not. So we don't go into the if statement. And then we're done with all the edges that are adjacent to C, which means we bump back out and we go find a new minimum. So let's look through the list. So we got D, E, and F are our options. So D is a 2, E is a 4, and F is a 2. So we kind of got a tie for minimum. So let's just do D. It doesn't really matter which one you do if they're both the minimum. So let's, oopsie. Let's get our, we take D out since it's the minimum, one of the minimums. And then we look at all the edges adjacent to D. So let's start with B. Is B in the queue? It's not, it's gone. Is C in the queue? Nope, it's gone. Is E in the queue? It is. Is E's key value less than, or no, is the edge of D to E, which is equal to 3, is that less than E's key value, which is 4? It is. So we need to go and update the E. So the parent of E turns into D, and the key of E turns into 3. That was a fun line. Yeah. So let's go into E. We found a slightly better path, more efficient path. So this is a 3 instead of a 4 now. That's a D. All right. And then D's also connected to F. Let's not forget about F. So let's check F. Is F in Q? It is. Is the DF path edge, whatever, which is equal to 1, is that less than F's current thing? Key value, which is 2? It is, so we update it. So the parent of F is going to be set to D, and the key, that was weird, of F is going to be set to 1 instead of 2. So let's go and update F. So new parent value of D, new key value of 1. Alright, and then that's all the nodes adjacent to D. So we pop back out, go find a minimum, and then right now it goes A, B, C, D's parent value is C, and then E goes to F, or E goes to D, and then F also goes to D right now. So that's our path right now. So we go find a new minimum between E and F, because that's the only things left in the queue over here, and that's going to be F, because F's a 1, so we look at F. Let's look at B first. So, is B in the queue? It isn't, don't care. Is D in the queue? It isn't, don't care. Is C in the queue? It isn't, don't care. Is E in the queue? It is still. So, we look at the EF edge, which is equal to 5. Is that less than E's current key value, which is 3? No, it's not. So we don't care, and then that's all the edges that are adjacent to F. Nothing changed. Oh, I forgot to eliminate F when we found out that it was the minimum. I'm supposed to do that earlier. So now the queue only has E, so finding the minimum is easy. It's E. And we're going to look at E, adjacent nodes. So we'll start with C. Is C in the queue? It isn't. Is D in the queue? It isn't. Is F in the queue? It isn't. So we can't do anything. We also eliminated this. And now that the queue is empty, we have our minimal search tree, or whatever it's called. So A goes off into nil because it's the root, and then B goes to A, and C goes to B, D goes to C, E goes to D, and F goes to D. So this is our that's our tree. So it goes A, goes to B, goes to C, goes to D, goes to E, which and then also goes to F. So that's our tree. And this should be, so this has a length of 1, this has a length of 3, 2, this is a 3, and this is a 1. So what's that total? 4, 8? No, 10. And yeah, that is the minimal, whatever it's called, the spanning tree, minimum spanning tree. And yeah, that's how you do it with Prim's algorithm.